Isn't the future awesome? Okay, right, coming up now we have Peter Wang, who's going to talk to us about fundamentals of vector computing, the role Python and Anaconda will play in shaping Web 3.0. Now, if you were present for Travis's keynote, you will understand how important to Python and the Python ecosystem Anaconda are. So please join me in welcoming Peter to the stage.
All right. Hi, everyone. OK, this is all set up for me. Let's see if this actually shows up. Great. So can everyone hear me all right? Can you guys hear me in the back? Yes? No, they're not? OK, yes. OK, great. So thank you all very much. I'm really glad to be here. And I've changed the title a smidge, just a little bit. But it'll still be about vectors. It'll still be about Python. So hopefully it's good enough, right? So I am the CEO and the co-founder of Anaconda. Travis is my co-founder. And today I'm going to take you a little bit through a journey about the past, the present, and the future. So why we created this stuff, how Python came to achieve such dominance in this space, and where we're at today, and what we see in terms of people using these technologies, and where I think things are going. So let's start off with, let's see here. There it is. So how did Python actually take over? So back in 2012, I had a thesis. After doing many years of consulting with Python and having been in the scientific Python community for many years, I saw that the world was starting to change in how it looked at computation. And the scientific computing tools that we were using to do vector computing, they were getting adopted in unlikely places. And so I had a thesis that I firmed up in 2012, and that thesis was that two disruptions were simultaneously happening. On the one hand, big data, big data, if you still remember that term, that was disrupting traditional data warehouses and analytics and business intelligence, things like that. And also cloud computing, and in particular vector computing hardware, GPUs, those were disrupting, dramatically changing the abilities of companies to make predictions, make next level kinds of predictions about their business. And also what I saw, though, at the time, the reason why Python was getting adopted was because a lot of the existing tools had issues with their NPS scores, right? They were not really well loved by many of the practitioners. Python was getting adopted by places, even though Python was free, you might say, well, maybe they're adopting Python because it's free. But the kinds of places where we saw Python being used, they had all the money in the world to pay for all the best tools, but none of those tools were as good as the open source stuff that was coming out of the scientific Python community. The other thing that I observed, another insight that I had, was that Python was not just another language. And if you hang around software developers too long, you're going to hear a lot of them talk about these different languages and frameworks, and they're always learning new things, and everybody's talking about what's the new framework, new. But actually, there's a lot of people in this world that want to program, that need to do some programming, that are not trying to learn a new language every 6 weeks, every 6 months. They just want to learn one language and be done with it, and then do everything they can with that language. And I would say uniquely among all languages that I had seen, Python was able to break into the business analyst and the Excel crowd in a way that C++ could not, in a way that Perl never did, right? So even though we might say Python has a competitor in Perl or Ruby or nowadays maybe Rust, actually in this particular way, it has no competitor in the fact that it can actually be used by 3 vastly different cohorts, by traditional software developers who may be doing Java and C++, by business analysts who are more familiar with Excel and Tableau, and by the data science crowd, which are PhDs who gave up on academia to go make a lot more money in industry, right? All these different people, whether we're using MATLAB or Tableau or C++, they can all sort of tolerate Python. Some of them may even grow to like Python. And this is a very, very interesting capability of the language. So to recap, why do I think Python took over? I think because it was easy to learn for many people, because there's this incredibly rich library ecosystem, because it was designed for readability, which means that people who were not so familiar with it could program by example. They could look at someone else's code and generally understand what's going on. And also the communities are pretty good. So these are really nice language features. There's also one additional really interesting language feature that many people don't talk about, but which is fundamental to Python's success. And that's that the Python interpreter, CPython, has a low-level C API that's incredibly powerful and allowed folks like Travis to build amazing extensions that ran at native speed. So we did not have to compromise ease of use. We did not have to compromise readability in order to get next generation low-level Fortran power. So this kind of capability, this is really why Python came to dominance. And so 10 years ago, shortly after we started the company Anaconda, or Continuum Analytics at the time, we created a community, meetups, conferences. So this is the first PyData meetup that we did in 2012. And we really saw there was a lot of nascent energy starting to show up around the use of Python for business data analysis, not just for scientific computing. And so over the last 10 years, and I mean very, very quickly over the last 5 years, we've seen Python just rocket to the forefront of the language rankings. So now, TOB ranks as the #1 language, is certainly the fastest growing. And this has all been great, and I think a lot of that has been fueled by the growth of data science and machine learning. So let's talk about that, right? So that's the past, that's how we got here. Let's talk about where we're at right now. How is data science being used and adopted in business? How is machine learning being operationalized, right? We're kind of in a transitional time right now. One thing we know is that you're not supposed to say big data anymore, right? Because that is not cool anymore. So don't say big data anymore. You can talk about streaming data. You can talk about graph data. You can talk about quantum NFT blockchains. Don't say big data anymore, because big data was 10 years ago. Now it's all AI ML. But actually what the big data transition and adoption really showed us was that the traditional business way of looking at IT, that way was very siloed. So if you go into a large business that has, let's say, thousands and thousands of employees, you will find this same structure across almost all of them. They will look at IT as having a software development component and an infrastructure kind of component. There's a separate data management aspect, and then analytics, whether it's sort of light business intelligence analytics or whether it's deep predictive analytics with tools like SAS, you have these 3 different silos. They're kind of 3 different worlds. And the problem is, each of these silos has exploded over the last 10 years. If you're in the IT space, you're seeing the move to cloud blow up all of your traditional ways of managing IT. If you're in the data space, you've seen streaming data, big data, all sorts of non-structured data blowing up the ways that you thought about managing your classic data warehouse. And if you're in the analytics side, of course, you've seen analytics go warp speed into now AI ML, right? So every single silo has blown up. And in the interstitial areas between the silos, you have new kinds of practices emerging in a grassroots style. So between the explosion of big data and cloud infrastructure management, you end up with sort of modern data engineering. And then between the analytics needs, high-end analytics, and the cloud and scalable IT and vector computing, you end up with this numerical computing layer that then kind of grew up and blossomed into what is now the modern open data science stack with tools like Python and R. So there's a great saying, a great quote that I love, which is that scientists progress by standing on each other's shoulders. Computer scientists progress by standing on each other's toes, right? Because they don't really learn from each other very much. It's much easier to say everyone else sucks, I'm genius, I'm going to start my new project. A fresh, clean GitHub repo is the happiest thing in the world until the first commit, right? So the issue here is that we now are in an era where we see so much of what we build on actually comes from the 1970s. It comes from 50 years ago. Look at this list of things. How many of these things are still part of how we think about computing? A lot of them, right? What ended up happening is that we had about 30 years of frozen computing and operating system paradigms because of an industry duopoly, let's say, between the x86 style processor architecture and PCs and the Windows computing stack. And now, of course, Linux also added to that, but it's still very much a PC-centric view of the world. And now we're in a post-PC era. We have so many things we're trying to do, essentially to paper over this stuff, right? But look at this. The C programming language is still only, 2 weeks ago, Rust was approved for the Linux kernel. Until then, it was built on 1972 technology, which is the C programming language, right? Spreadsheets, Excel, is still the most dominant programming tool in the world. It's essentially a very close cousin, or it's a descendant of VisiCalc, invented in 1978. So really, in this day and age, when we look at all of the different tools we might use for managing compute, for scaling things, all of that stuff, nowadays, we are really papering over these broken abstractions. We're trying to bridge into a new paradigm by putting containers and containers and containers. And the question of what we actually have to solve, the problem we really need to solve, is how do we move past, go back here, how do we move past these silos, right? How do we move past these silos? Because these things are not separate from each other anymore. These all come together to form holistic capabilities and present us with new unified problems. So I did a podcast with the Andreessen Horowitz folks, I guess maybe a year ago, and I made two fundamental points in there. One of the points I made was that we should actually even stop thinking about data as this static thing. I know there's a famous quote that's been going around that data is the new oil, and of course I imagine this part of the world, right, it seems like, oh, oil is a very great source of wealth. But actually, if you think of data as a static thing, and you try to manage it, contain it, bottle it up, you're actually going to be building all sorts of bad ideas in. You have to view data as live. You have to view data as rich, as an evolving thing, and you have to understand that data is never raw. Every single piece of data you get comes from a gigantic pile of hardware and software that produces that data observation. So that's why I say data is actually just frozen models. And if you don't understand the models that produce the data, you're not going to be able to fully understand how to take the data forward to build new models. And the second thing I said is that in this new post-PC era, in this new ML era, we have to rethink all of the ways that we've thought about managing computing and managing enterprise IT. We actually have to understand that functional correctness now is no longer enough. It's actually evolved to be dependent on the data inputs. And just like Niels was saying, right, what is ML ops? ML ops, you have to be aware of the data. The data actually flows into the code, and you have to manage these things together. Exact same concept here. You can no longer just write unit tests for some simple transformation functions. You actually have to think about what data did it come from? At the time that we built this thing, what do we assume the reality of the world was? All of these things are actually essentially live information systems. And so the issue with all of this, though, is that most businesses are used to adopting technology in, well, a frozen way, in a way that's been baked in for 30 or 40 years. And this really bright guy, Paco Nathan, had a series of tweets that were absolutely brilliant a while ago, earlier this year. And he talks about the fact that these IT practices leverage these fragmented, these frameworks, and the frameworks get very big, and priesthoods develop around them. And so at that point, they're no longer really open source, they're not flexible, they're not agile. And so what I've come to learn in the last 10 years is that the way enterprises adopt technology and the way they operationalize technology is more a function about the structure of the enterprise IT organizations. As long as you have a separate infrastructure team, which is separate from the data team, which is separate from the code teams, and they all roll up to different VPs with competing agendas, you're never going to be able to build a holistic system. It takes someone who is in a line of business, that has a business stakeholder who cares about the whole unified information system to drive that change to the organization. So the other thing that we realized was that at this point in time, large companies, they can afford to really be ineffective because they don't have much competition, and there's a lot of internal power dynamics and things like that. So as an open source innovator guy, when we try to push our stuff into these kinds of companies, what we see is that we run into these kinds of dynamics, right? People build priesthoods in order to defend their careers, not to actually advance the state of the art within their businesses. So for all of you who might think of yourselves as innovators who are trying to do work in cutting edge areas like this is just a thing to be aware of. I'm just sharing with you an observation, right? So there's a quote, a great quote about how like every gazelle wakes up on the African savannah has to run faster than the fastest lion or whatever. And what I realized in enterprises, actually people don't get fired as long as the enterprise is like making some money, right? And so what this really means is, and building upon this, another thing that sort of got me a little more depressed was realizing that when we talk about the innovator's dilemma, or we talk about, the chasm crossing, the chasm of adoption, or the hype cycle of technology, as Gartner likes to call it, what I realized was that as we create more technology innovation, there will be more ignorance, right? If you create a new thing, some people know it, the vast majority of people don't know it. And in this gap between the people who know something, the clueful, and the clueless, inside this gap, a lot of hype, a lot of nonsense, a lot of BS will fill in. And there are many people who will do that, and they make a career of doing it. And so what I realized is that because open source allows us to be much more creative, much more innovative, much faster, we're going to be creating a widening gap into which an increasing amount of BS can fill. And that's why I say this is a semi-permanent problem, and I'm not even sure how to solve it, but at least calling it out, naming the problem, is the first step. So I sort of threw a tongue-in-cheek sort of slide in here about, if you're familiar with Conway's Law,
what I realized was that the architecture of business data systems actually reflects the budget structure of the IT teams that manage it, not any actual underlying principle, right? Not technical excellence, nothing like that. But a less snarky way to put this is this observation that there are really two fundamentally different kinds of people in this world. There are people who are pioneers and people who are settlers. And within businesses, you'll find, especially established businesses that are risk adverse, that have organizational structures that are very risk adverse, you'll find that they have very much a settler mentality, and they always have excuses not to do and try new interesting things because there's risk involved. There's always risk involved. Risk management is the name of the game. But pioneers are always out there. They see risk as opportunity. They see the boundary, the frontier, as new places to find interesting things. So these are really two fundamentally different things. And the issue is, the reason why I bring up this concept in a talk about AI and ML is that what you end up finding is if you really do data science, if you really do machine learning, you are in a pioneering space. You need pioneer mindset people. And those people will always have a culture clash with a lot of the settler people who are maintaining the classic old systems. So let me recap that. We are now in a transitional era of IT systems where we have to build new holistic systems driven by a pioneering mentality. And those old enterprise silos are maintained by people with a settler mentality. And so there is not only technology difference between these folks, but there's actually a culture and even a personality difference. So that's something else for you to be aware of as you roll into this. So one of the things that you hear a lot when you talk to people who manage kind of the settler mentality kind of folks, they talk about scale a lot. They talk about, is it scalable? How do we manage this at scale, right? That's a term that people throw around a lot when they talk about productionizing and operationalizing things. And sometimes it comes from a very good place, but sometimes it's just an excuse. Because the way that the last 30 years of software development and IT management has scaled in the PC era and in sort of the server cloud 2.0 era, or web 2.0 era, the way we've scaled is most large organizations have adopted lowest common denominator technologies, and they've scaled with headcount. But in the open source world, in the innovation world, we scale not that way at all. We scale by allowing trustful networked communication between high capability individuals. So we really put a lot of emphasis on individual capability, individual innovation, individual capacity. And it's a different kind of scale. It's a network scale between really, really bright individuals versus scaling by just cranking headcount on the lowest common denominator. Very, very different worlds. And the issue is, as we go into a world of ML and AI, how do we avoid carrying this particular, what I call the original sin of enterprise software development, how do we avoid carrying this forward, right? Because the future that we have is a cybernetic one. The future that we're steering right into is one where we are doing online computation and prediction. So to understand why I use the word cybernetics, I want to sort of do a small little history lesson, which is where computing actually came from. Computing and early computers in the early 20th century or mid-20th century, they all started with prediction. The earliest computers, what we would think of computers as today computers, many of them were used in things like Navy battleships, right, to control the angle of the cannon. This picture here is one of the targeting computers for the cannon, for one of the main guns of a US battleship called the Iowa-class battleship. And so prediction really, so computing started fundamentally with doing online prediction. And then we moved from prediction in post-World War II to building mainframes that could just count things. Tabulation, counting, statistics, these started becoming the dominant thing. And then with the PC revolution and with global telecommunications and banking and finance all using these things, starting in the 1970s, 80s, transactional systems dominated. And prediction became very niche, except in a few areas. Finance still used prediction, credit card companies, insurance companies, certainly the Department of Defense and the military used prediction, but almost all the computing everywhere else became just transactional tabulation. But now, in the last 15 or so years, 20 years, we've seen that with the advent of personalized, hyper-personalized computing with smartphones and social media and e-commerce globally everywhere, we see now prediction being a driver once more. And so now not only are we building prediction to make just a static prediction, we're actually building prediction and wiring it directly into a sensor or an actuator, or wiring it into an advertising system, or wiring it into a song recommendation for an automatic playlist. So we're now taking prediction and wiring it into action, and that is the definition of cybernetics. So when we were trying to build these cybernetic systems, we have to have a holistic approach. We have to actually look at the code and the data and the problem we're trying to solve and all of the human biases and human heuristics that were brought into asking the questions the way we ask them. So correctness now is multidimensional. It's beyond any individual component. You can have a cybernetic system that has functional unit tests that pass, that has data that is clean and schematized, and the whole system you put it together, and it's still a wrong cybernetic system. It still fails as a model because it's predicting the wrong things. So this is the kind of thing that is completely game-changing. It's completely transformational. The entire industry, every single business that wants to still be around in 10 years has to actually start changing itself along these lines if it's going to operationalize machine learning for anything that it does seriously. And this ties into then something sort of building on an earlier point. It's just as we have to have these systems be holistic, we also are trying to, one of the things we're doing here is we need to actually put all this capability together, this cybernetic sort of capability. We have to put this directly in front of the business stakeholder, directly in front of the domain expert, the person who understands what we're even doing the computing for, right? If you look back at this picture, the people who built this targeting computer for this cannon, they were talking to actual sailors. They were talking to actual naval tacticians to figure out what they needed to do. They couldn't just go and build some automated targeting system in a black box over here and then roll it onto a battleship and hope for it to work, right? That would never work. And so when we build cybernetic systems in every business, we actually have to bring this closer and closer and closer to the business stakeholder. We have to bring it closer to the scientist, the quant, the doctor, whatever it might be. And so this is not just a one-way street, though. It's a two-way street. All of these people who want to use cybernetic systems, all these people who want to use machine learning and AI, they also have to move closer to understanding the statistics. They have to move closer to understanding at least the basics of how some of this data is prepped and how some of these systems are built and deployed and what their limitations are. And so this comes full circle back to why I think Python is such a foundationally important thing. You know, you might say, well, Peter, that's just a language. There's many languages. It could be C++, it could be C#, it could be JavaScript. And I would say, actually, no. Language is not the same. Language for humans is not the same as language for computers. If you look at human languages, the vast majority of people on this planet speak one native language. Many of them may speak two, but the vast majority speak one because there's a network effect to it. It's really important that all the people in the team can speak the same language. It's really important for that language to actually empower them to think about their, to improve the scope of their consciousness and to improve how large of a space they can reason in. Python, as a language that's easy to use, as a language where it's easy to model the primitives of your domain problem, Python is actually this kind of extension, has this extension capability. There's a great good friend of mine who's a renowned SciPy contributor in the Python ecosystem. His name is Robert Kern. And 15 years ago it was that he said, the reason I like Python is because it just fits in my head and it gets out of my way. And that's a really powerful concept. Now, he was a geophysicist from Caltech, so his head was bigger than most. But nonetheless, the idea that this language gets out of your way and lets you express your ideas is really, really important. And Python as a language, I think people have voted with their feet. You see educators teaching it to children. You see many people who are not traditional software developers taking bootcamp courses or watching online videos on the weekends to try to learn a little bit about AI and ML with this Python stuff in a Jupyter notebook. This idea that a computer language, is not there just to make a computer twiddle some bits correctly, but actually can improve your ability to think. That it's actually more an extension of the human mind than it is some scripting of a computer capability. That's a really different paradigm, and that's one that, well, you saw Fabio's talk earlier about PyScript. That's something that we care a lot about at Anaconda. That's something I personally care a lot about, because this is actually a really, really stark situation we have today. If you think about how many programmers there are in the world today, some people say, well, there's a few million. Others say there's tens of millions. By any measure, there's no more than 30 or 40 million programmers in the world. And those blue boxes, everyone is a programmer. Everyone is a million programmers. The gray boxes are the 8 billion other people who don't know how to program. And so as we enter into a world where machine learning, where AI literally powers every single decision, every single thing that happens to us, right? Cars, self-driving cars, delivery drones, e-commerce, social media, automated dictation, and automated speech sort of synthesis, art. Everything will have cybernetic systems behind them. And if we have a world where less than 0.5% of the population can even understand what those systems are doing, that kind of world by construction is a problematic world. That kind of world by construction is set up for really, really, really problematic power structures. So it is so important for us to empower everyone else there. Just like we teach people how to read and write in a language, just like we teach people how to do math. Teaching students, teaching children how to understand computers, how to work with cybernetic systems, understand their limitations and their power. This is absolutely foundationally important. We need to have a world where every single member of the UN understands code, understands not how to do low-level code, they don't need that, but they need to understand the limitations, because if they don't, they'll be surrounded by ministers and lobbyists who make all sorts of promises that are completely false, and they won't be able to tell the difference. They'll be in the chasm of ignorance. All of us here who show up at conferences like this, all of us here who are learning how to program, who are building MLAI systems, we are pulling the edge of innovation further and further away from the mass of ignorance. Ignorance is not a judgmental term. It's a statement of fact. These people do not know how to do it. They don't know what's good, what's bad, what's crap, what's real. And we're pulling the frontier even further away from them. So it's really, really important for us to actually call this out as a first-class problem and invest into it as a first-class concern. Because the future of the world is one where every single decision will be augmented with computers. The future of the world is computational decisioning. Whether you believe there's going to be artificial general intelligence, whether you think there's a singularity or not, what you can probably absolutely believe is that every single decision that ties to a bit of silicon in about 10 years' time is going to be powered by some kind of model, some kind of self-learning, self-training sort of thing. And that's going to allow these decision loops to run faster and faster and faster. Businesses that don't adopt this will die. They will be destroyed by startups that do. And so we're going to see a complete transformation of the world into the world of cybernetics over the next 10 years. That's going to be what the 2020s are about. And so for all of you who are practitioners who want to reduce some of this to practice, one last takeaway I'll give you is how to think about how do we actually know what's good? Even if we're practitioners, even if we're trying to learn in this space, how do we know what's good and what's right and where things are actually going? And so there's 3 fundamental points. One of them is you should understand data. You should know that there is no such thing as data. Behind every data is a frozen model, right? Even if you take your smartphone, you take a picture. That picture now goes through AI software inside the phone. Before the AI software has a chance to touch it, it goes through a lot of digital signal processing to turn the grayscale pixels into red, green, blue. There are models upon models upon models, even before you get the raw input data into your database. So we need to think about data as not a static thing, not an oil to be pumped out or to be extracted from people. Data is simply a interstitial representation of one set of models interconnecting to another set of models. Second, we should understand what the computer is. Computers are not just PCs anymore. It's not just a chip and some RAM and disk and network, right? Computers can be tiny embedded things that are the size of my finger. They can be giant, vast warehouses of massive compute power. But at the end of the day, you will never make headway unless you understand what your actual computer can do and what it can't do. You can buy into frameworks. You can go and spend a ton of money with cloud hyperscalers who promise you the moon. None of it makes any sense unless you understand what the actual raw compute power is of your machine. And one of the most fundamental things you should think about, and one of the most fundamental things you have to understand, is bandwidth. Not abstractions, not frameworks. You can always put more and more frameworks on top to paper over something that's difficult, but what actually limits performance at the end of the day is bandwidth. So understand what is the throughput capability of the processors you're using. Understand what is the throughput capability of throughput and latency of the network connections that you're using. That's how you have to understand the computers. And lastly, you have to understand that all of these things, all these technologies, only get adopted in the context of people and groups of people deciding to adopt them. So all of you who work for an organization of any sort, you should understand that as we're moving faster and faster into this really different and strange new world, as we're essentially transitioning through past 40 or 50 years of stagnant paradigms, you have to help the people in your organization make that bridge as well. You have to help them make that transition, right? And also a really important thing is the word scale. Smart people don't scale. Organizations that insist on being smarter by scaling smart people, they have to empower those smart people. they cannot try to make those smart people dumber and scale dumb people. 10,000 stupid people is not as good as one smart person if the smart person knows how to solve the problem and none of the 10,000 dumb people don't, right? So this is really, really important as we move into an era of accelerated cybernetic innovation. And lastly, and a point I didn't get too much into here, but this idea of systems being engineered to have slack. Systems being engineered to not be hyper-efficient, but actually to have room for creativity, for pioneers to explore, to make not mistakes, but to build little prototypes that don't work out, right? This is actually the kind of world we need. This is actually the kind of technology posture every business has to take. So anyway, on that, thank you very much. That's the end of my talk. Do we have time for questions?
You caught me by surprise, Peter. Perfect timing, perfect timing. We have a few minutes for questions if anyone would like to ask any.
Hello? Hi, okay. Thank you for the great talk. You put it beautifully like a storytelling kind of approach from history to now. And you talked about data in the enterprise. And I work in a bank, and I know how difficult that is to get data to become very valuable in a bank setting. And I think, as you put it, the way that you get value from data in an enterprise is basically knowing the data, knowing how to, the domain knowledge of the data, knowing how to model it properly, and then use basically Python data science and predictive modeling to achieve business outcomes. Lots of the data in traditional enterprises are in databases, of course. And I see like SQL and Python work beautifully together.
Yes, they do, right.
Yes. So do you think there will be more sort of synergy between SQL and Python in the future? Or, I mean, it exists sort of today.
Absolutely, absolutely. The reason why SQL is so important is not just because so many business processes are, have 40 years of business processes have been built around SQL. It's that SQL actually has been the ultimate arbiter of truth for many of these information systems for so long. So the SQL is actually itself, at a meta level, it's a journal of the business model and the business decisions, right? And it can be gnarly when you look at thousands of databases with millions of rows of data and all these different kinds of schemas. It can be a little frustrating sometimes. But at the end of the day, the SQL is how the business runs. And so it would be completely intractable to think that we could replace all of this with Python or something else like that. And there'd be no need to. SQL is very good for expressing what it expresses. That being said, Python is very good for expressing what Python expresses, right? So we want to bring these two worlds together. And there's many, many kinds of interesting, exciting things happening around this. The first, of course, is the fact that if you use SQL, and if you want to do cloud databases, a great way to do Python and SQL is to use the Anaconda in Snowflake. So we have, it's not quite GA yet, it'll be GA sort of end of the year, but we have the ability for you to run Python, pandas, scikit-learn, all these things, TensorFlow. You can do Python natively inside the database on a table or on a row basis. You can write UDFs in Python. And so this took a lot of effort, and there's a partnership between Anaconda and Snowflake to allow so many of these Python data scientists and machine learning engineers to then work directly inside the SQL database, right? So there's no separation between the transactional store and the analytical store. Now that's, of course, one particular vendor, one particular solution. If you look at other things, if you look at the rise of the popularity of DuckDB or IBIS or things like that, what you're seeing is this tendency to move Python and move the Python code, the domain expression of the question, to the SQL, to the database, to the actual store of records, or the store of record, if you will, yes. Right? And so that moving code to data, moving questions to data is a paradigm that we're going to see over and over and over. So I would recommend looking at things like that. But I absolutely see a world of the future where Python and SQL will just get better and better with each other.
Okay, great. Thank you.
Thank you.
Hello. I apologize in advance, but I caught a bit of a paradox in the talk.
Okay.
You mentioned people stepping on each other's toes.
Sorry, can you say that again?
People stepping on each other's toes.
Yes.
An empty GitHub bit. But there's also a lot of talk about, leave the smart people to do the smart people stuff. Who decides who the smart people are, and how do we? Do you see the bit of the problem here, or do I need to explain?
No, could you explain that a little bit more for me?
All right. So, yeah, there's a bit, you mentioned the problem. There was a slide where there's few coders existed and the greater ignorant population out there. There's a power dynamic involved in knowledge, intelligence, and all of this stuff.
Yes.
Yeah. So, and part of that power dynamic is who decides who's smart. Because if you want to set people up for positions of power, decision making is power.
Yes.
Who decides who these people are? Who does this? Other smart people? How do we decide if NumPy or Panda or Beta is the best one outside of results, data? Right? Who decides?
Well, that's just it. Actually, you've answered your own question.
Okay.
Yeah, because there's a lot of current. I don't think I'm going to surprise anyone by saying that a lot of business activity in this world is centered around not data. It's centered around egos. It's centered around confidence schemes. It's centered around BS embedded in PowerPoints, right? And so those kinds of people who do that kind of activity are not qualified to determine what the smart people are. And in fact, what normally happens in most businesses, based on what I've seen in my consultancy years, is that the smart people get some work done in spite of those people, right? But we're now moving to an era where smart people can empower themselves. They can find resources to go and build startups, build things on the side that move faster. So the way that I would say the way that you solve this problem is not top down. It's actually it emerges. There's a term called stigmergetic or stigmergy, where this emerges, right? And so who decided NumPy was better than, I guess, not NumPy? It was actually the users voting with their feet. It was all the other makers of the tools, right? And pandas, at the time that pandas emerged, there were 6 other competing labeled array data frame libraries for Python. And eventually the ecosystem coalesced and converged around pandas, right? Pandas was good, but it certainly had its deficiencies at the time. But because the creator of pandas was working so hard, was so responsive, and just did the work, everyone else gravitated around him and said, well, look, pandas seems to be the thing, right? So what we have in the open source ecosystem around Python and around PyData, we had an emergence from pioneers voting kind of in their own way, and it wasn't some priest inside the city in the settler camp who said, you, because you're my son-in-law, right? You're the smart guy. So in a sense, and I didn't want to get too political in this, maybe I've already gotten too political, but in a sense, if we empower smart people, and I'm trying to encourage all the smart people in the room to own this problem. You are the change you want to see in the world, right? Be the pioneer. Do something bold and entrepreneurial, and see if you can't coalesce other people around you, and then they will know you by the impact you have.
Thank you very much, Peter. What a great story.